Hello, everyone. My name is Tianyi Zhang, and I'm an assistant professor in the Department of Computer Science at Purdue University. Today, I want to tell you a little bit about SecureChain Knowledge Graph from the NSF Proto-OKN program. The motivation behind this project is the increasing number of software supply chain attacks in recent years. Because of the interconnected nature of modern software, the vulnerabilities or malicious code can spread very quickly in software ecosystems. So there is a pressing need to address this cybersecurity threat. Existing tools for software component analysis and vulnerability dependency detection have several limitations. First, most of these tools only check direct dependencies. They have limited support for transitive dependencies. In other words, if your software depends on one package that itself also depends on another vulnerable package, then today's tools usually miss these risks from this indirect dependency. Second, these tools only rely on a narrow set of cyber intelligence sources, often excluding timely information from informal security reports and social media. And third, they provide limited support for C and C++, which is the most prominent programming language that accounts for almost half of the known vulnerabilities today. And finally, they do not provide a global view of the vulnerability propagation. So security experts have a hard time tracing how a single upstream vulnerability can cascade across the downstream packages and applications. Together, these limitations highlight the urgent needs for a more comprehensive, dynamic, and cross-ecosystem solution. Our solution is to develop a large-scale knowledge graph that captures the entire network of existing software components available on the market, including their direct and indirect dependencies, and also, the vulnerabilities associated with these components. So when a new cyber incident occurs, we can quickly perform a whole graph analysis and model all the vulnerability propagation paths so we can make a comprehensive risk assessment and also make an informed decision to contain and reduce the damage caused by this incident. And here is a formal definition of our knowledge graph. Our ontology, sorry. Our ontology is built upon schema.org. We reused existing classes and properties from schema.org as much as we can, so it can be easier to connect with other knowledge graphs who also use schema.org. And we also extended some of them to support some domain-specific nodes and predicates in our knowledge graph. SecureChain is built on multiple authoritative and real-time data sources. This includes the CVE list, the online project repositories on GitHub and Debian, software package managers, cybersecurity advisories from federal agencies, and also cybersecurity news articles. Currently, SecureChain tracks over 12 million software components, 461 million dependencies, and 259,000 vulnerabilities across 7 popular programming languages. So how do we build a secure chain? First, we developed rule-based data extraction scripts to extract knowledge triples about vulnerability and software dependencies from structured data sources like the CVE list and the package managers. And then for those online code repositories on GitHub and Debian, we developed program analysis tools to perform software component analysis and extract software dependencies. And finally, to capture insight from unstructured data like news articles, we developed an LLM-based pipeline that recognizes software and vulnerabilities mentioned in an article and extracts them as knowledge triples. In the next few slides, I want to tell you a little bit more about this LLM-based knowledge extraction pipeline, because I think this is the most interesting and the most challenging part of this project, given all the complexity and ambiguity in natural language documents. And I also believe many of you may also find these techniques relevant in your own domain, since using large language models today for natural language processing has become a pretty popular and essential skills today. One challenge we face is to recognize the domain-specific entities related to software, hardware, and their vulnerabilities. Even though LLMs today are pre-trained on enormous data from the internet, they sometimes struggle with concepts and terminologies in highly specialized domain. So we decided to fine-tune language models to recognize those specific names in software ecosystems and cybersecurity. Of course, to fine-tune a large language model, we need a lot of data. So we leverage a software entity recognition data set we curated from Wikipedia called Wiki SER. And we also use GPT 3.5 to generate a bunch of synthetic data. And regarding the model architecture, we decide to go with an ensemble method where we fine-tuned both a large language model using the universal NER framework and also a relatively small BERT model. This is really because we find that large language models and small language models actually exhibit different NER capabilities, name entity recognition capabilities, and they do not really always overlap with each other. So we want to really combine them together. And the results looks quite promising. Our method achieves about 90% of precision and about 85% recall on average. So after recognizing the entity names, we need to infer their relationship, like which software is vulnerable to which vulnerability. In this step, we choose to directly prompt the large language model since, because the relationships from SecureChain are relatively simple. And we found that LLM's innate capability is sufficient for this task. And you may already notice that our methods in the previous two steps are not 100% accurate. So to handle this issue, we introduce a knowledge validation mechanism. And the basic idea here is to ask the language model to reflect on the original article it receives, and then based on the reflection, double check whether the extracting knowledge triple is correct. And finally, this validated knowledge triples need to be merged into the knowledge graph. As you may recall, we actually extract knowledge triples from other data sources like the CVE list. And those knowledge triples may actually mention the same software or vulnerability entity with slightly different naming conventions. So in order to merge them, we need to first check the entities in different knowledge triples refer to the same entity, which is typically known as the entity resolution in knowledge engineering. So here we develop an embedding-based method to achieve this. Basically, we're going to encode this entity mentions and their surrounding sentence, the preceding and the post sentence, which is known as context, using an embedding model, and then compare the cosine similarity of this embedding vectors. And to evaluate the performance of our knowledge extraction pipeline, we sampled 1,000 outposts of each stage in the pipeline and manually examined their accuracy. Overall, we find that the accuracy is quite reasonable, especially given the scale and the complexity of this online data sources. We also did a little bit of failure analysis, and we found that the majority of the inaccurate triples are from the NER model in the very first step. Even after fine-tuning, the NER model still extracts some generic terms like malicious code and elevation of privilege, which are not specific enough to be included in our knowledge graph. SecureChain supports a wide range of use cases like cyber risk assessment, automated vulnerability monitoring, SPOM construction and validation, and patch prioritization. Its value also extends across multiple user groups like security researchers who want to develop new cybersecurity tools, industry practitioners like software vendors, cloud providers, and small businesses who want to meet the new SPOM requirements and audit their software, and also government and defense agencies who want to perform national cyber risk assessment and make quick responses to cyber incidents. Here, I want to show you one example about a vulnerability in network communication library called OpenSSL. SecureChain can trace not only the direct impact of this vulnerability, but also how this vulnerability propagates into hundreds of downstream applications like Android SDK, NDK, MySQL, Docker, and Google Cloud. So this actually provides a clear picture of the real-world impact and helps prioritize strategies to contain and fix this vulnerability. If you are interested in learning more about the SecureChain, you can find the details in our project website. We have also open sourced SecureChain on GitHub. You can find all the data, ontology, and the knowledge extraction scripts there. And if you are interested in testing SecureChain online, you can use the Sparkle query interface from Frank. It's completely online, and you don't have to install anything on your laptop. Here is a screenshot of the online Sparkle query interface on Frank. You can write the Sparkle query in this online editor, and then click on this Run button to see the results. If you are not familiar with Sparkle, don't worry about it. We also designed a visual query interface where you can write a query using a visual block language similar to Scratch. It's like playing a Lego game where you can drag and drop different building blocks, and each block here basically represents a Sparkle query operator, like a match or a predicate in the knowledge graph. In this way, you don't have to memorize all the syntax details in the Sparkle, and you only need to drag and drop. Now let's look at how SecureChain fits into the big picture of Proto-OKN. SecureChain is one of the 13 knowledge graphs in the Proto-OKN ecosystem. It is stored and federated in the Frank infrastructure, and you can access it through the OKN API toolkit or through the online user query interface developed by Spider. And we are also working with the Spider team to integrate the Sparkle query visualization we developed to help non-experts understand and debug the auto-generated Sparkle queries. SecureChain can also complement other Proto-OKN experts in domains such as climate change and healthcare, which increasingly depend on complex software for computation. For example, we have used SecureChain to check the climate models from the Climate Pub for KJ knowledge graph. And our analysis revealed 24 vulnerable Python dependencies with 145 known vulnerabilities, demonstrating the importance of securing the supply chain behind critical scientific software. And also, we are working with the SecureChain team to develop a joint knowledge graph for semiconductor supply chain security. This work extends SecureChain's methods to cover vulnerabilities in semiconductor products such as GPUs, CPUs, and memory components. And currently, this knowledge graph tracks over 5,000 vulnerabilities associated with the semiconductor products from 239 companies like Intel, NVIDIA, and Qualcomm. Finally, our long-term vision is to grow SecureChain into a sustainable and also the largest open source ecosystem for supply chain security. And this ecosystem will include not only the knowledge graph itself, but also a suite of security tools built on top of the knowledge graph. And currently, we are collaborating with Red Hat, BAE Systems, and Lockheed Martin to co-develop these tools. At the same time, we hope the broad open source community can help us enrich the SecureChain's data sources by integrating cyber intelligence from well-known blogs and social media accounts. Through these efforts, SecureChain will evolve from a research prototype into a community-driven platform that continuously monitors critical cyber infrastructures 24/7 and expands its impact across national security, industry, and academia. Thank you.